Hello and welcome back to Calculus2. We are looking into second part of integration by parts. We're just going to do extra exercises, and then you can find much more obviously online. And if you read your textbook, some examples are worked out. So the first exercise is going to be the exercise 18, which says integral of sine inverse of x dx. So what do you think? What should we do?
You should use the formula of like 1 divided by square root 1 minus x squared.
You are going to get that.
Like that's like remember this type of formula. I mean, this type of pattern. It's very, very, very long.
Yeah, but it's not. So stuff like this is generally not on the exam for those kind of reasons, right? Because you can look it up when it runs out.
And I know I had to do this one like at the end.
So what is u? Very good. Arc sine of x. And what is dv? dx. Good. So what's du?
1 over the root of 1 minus x squared.
And what is v? X. So it's x. What?
This one try to solve it.
No, okay. Got it?
I got a quick question about this. Basically, when you do like a double integral, what happens when you have to do like a double? You get the how would you do? What would happen with inside that integration? Would it still be the same or different?
It will be different because the first integration that you got when you did the integration by parts, the first time, the integral that you get still has to be using the integration by parts. So you still can't integrate. You have to. But sometimes what's going to happen is, like in this case, what do we have to use here?
I saw it's like 1/2 x squared times negative first power. But I thought you could do u equals x, dv equals 1 minus x squared.
We don't have to use anymore.
Yeah.
This is it. This is the end.
No,
This is the guys. Too much noise.
That's actually not what the book says. It says x sine inverse x plus by square root 1 minus x squared plus by c.
Yeah, but you have to. How do you solve this integral?
By doing sine inverse.
No. The integral here, the one that needs to be done now.
Just do u equals x.
No, that will be another u sub. We have a u sub now. This is the Calc1 integral now. U equals, yes, 1 minus x squared. And then du is negative 2x dx. Now, what I said earlier is, anytime you see integral on a page, you first say, is this basic integral? If it's not, then you ask yourself, it is u sub. If it's not, is it by parts? So, we started here. Is it a basic integral? No. Can we do u sub? No. By parts, right? You do by parts, and then you get this integral. Is it a basic integral? No. Can I do u sub? Yes.
How can you tell when it's basic or not?
Basic is on the list. Sine, cosine, x squared, right? The basic integrals. So when you have the basic functions that you know from the list, right? That are in basic integrals are listed. The list of basic integrals is given in 7.1 on the chart. So you have to know. Oh, you have it. Nice. The list of basic integrals is the ones that we memorized. That's given in a textbook. So if it's not on the list of basic integrals, then you ask yourself, is it a u sub? If it's not a u sub, then is it by parts? The same thing you did with the derivatives. Is it a basic derivative? No. Okay. Chain rule, product rule, quotient, which one, right? So if it's not a basic integral, then what method? And you always ask yourself, is it a u sub? That's what it starts. So now that we are working on this problem, we're doing u sub. I need to fix this. I need negative 2x and negative 1 over 2 over here. Not negative 2x, negative 2. And then I need a negative 1/2 to change that into a plus. So now I have x sine inverse x plus 1/2 integral du over square root of u. I can write it as u to the negative 1/2 du plus 1/2 u to the 1/2 divided by 1/2, right? So now these cancel. Plus c. Don't forget plus c's. I hope you put those on the test. Pretty sure you forgot 6 of those. That's -6, but then good thing that quizzes are covering it, right? If I had 10 cents for each plus C I forgot when I took calculus, I would right now have 20 cents.
I love the build up. I would now have 20 cents.
That's the truth. All right, I believe this is it. Do we all have this? Right? So this is how those big formulas in the textbook, right? At the end of the textbook, you have 106 different formulas. Most of them, not most, but some of them, or maybe even most, can be proven using this, right? All right. Off we go with the next example.
Got a quick question.
Yes.
About this. So what happened to the one on the very tippy top that says x sine inverse of x? What happened to that other one?
Okay, which one?
Up.
More up?
Yeah. That one pretty much. What would happen?
This one? This one is that one. And then we did the 5 parts and we got to this point. So this is u times v minus integral of v du, which is this times this, that's over that. So you have to understand this one is not that one. This is not that. This is the one from here.
It's a different one.
Yeah.
Like this. Like you're doing something different.
What's the formula? Look. uv, right? Minus integral of v du. It's the formula, right, for integration by parts. You just plug everything where it belongs. One variable at a time. Let's do another one. Let's see. Oh, we never did any of these. Ready? Super. You're going to love it. So far, all problems we did were improper integrals. No, improper integrals, indefinite integrals. Definite integrals have limits, and you can convert the limits to compute, depending on where you are, if you have to use another u sub, right? So let's see. Let's start with the first example, the simplest example. Integral 1 to e ln 2x dx. So you know how to integrate this, hopefully.
I thought it's like on over x, but it's not like that.
The derivative would be Yes. I had a lot of time on my hands to practice. No. Later. I can also move just one arm. Look at the other one. Um, did you take the derivative?
Yeah.
Did you get ln 2x?
So this was a warm-up problem, and you have to compute the limits in both parts once you integrate everything. So the good old u is equal to ln 2x, dv is dx, du is 1 over x when the 2's cancel, and v is x. And we set up the formula. So we have x ln 2x minus the integral of just dx. Oops, I forgot the dx over here. Courtyard. There we go. So 1 over x and x cancel, so we just get this. And we still have the limits 1 to e. So we have x ln 2x minus x computed from 1 to e. So this is e ln 2e minus e minus ln 2 plus 1. And then we simplify. So ln of 2e is going to be e. No, it's not e squared, it's 2e. So it's ln of 2 plus ln of e minus ln 2 plus 1. So we have e ln 2 plus e minus e, they cancel, minus ln 2 plus 1. So ln e is 1 times e, it gives me this e, so minus e, good. So now we have factored out ln 2. We're left with e minus 1 and then plus 1. So probably, you know, this is what you type in as the exact answer for your homework.
I still don't understand. Can that be wrong anyways? Like basically, how were you able to determine where you have to like place in the e and the 1? Because I thought you could do ln e squared for instance, cancel the e.
Yeah, but because they're different. ln of 2e is ln 2 plus ln e, and ln e squared is 2 ln e, which is 2 times 1 is 2. So this is well, I can write it like this. It's different rules, right? One is the product, and the other one is the exponent. That's from Pre-Calc 1, Chapter 3. Well, in this school. All right. And another one, because these are so awesome. X cosine 2x 0 to pi over 2. Got it?
We switch up. But you can't have, like, I took Calculus 2 twice. Basically, I took all the stuff already.
And I think we were the ones that sat back in class and pretended students the first day. We said one of them came up to us afterwards, like, are you guys going to class today? It's like 4:15, and we're up in the library, we're not in class. So you didn't get that when we like said hello and welcome back to Calculus 1 and got up and left. Cool. Yeah. I got to it.
But this one takes a 0. I got parsing 0.
Yeah.
Yes. Has to be. I'm in. And to the pi over 2, yes.
Why do you like cosine?
It actually will still, it will still give you your
Can't.
All right. U equals x. dv equals cosine 2x dx. du equals dx. V equals integral of cosine is? Very good. Sine 2x over 2. And then we use the formula. All right, so what do we have? uv, which is 1/2 x sine 2x minus the integral of, we can kick 1/2 outside, sine 2x dx. And now when you integrate, we get 1/2 x pi over 2, right? 2x. Minus, when you integrate sine, you're going to get negative cosine, so that changes to plus. Another half drops out, so it's a quarter now. Cosine 2x from 0 to pi over 2. So now when you plug in pi over 2 into the first one, you get 1/2, well, you get pi over 4 actually, sine of pi plus 1/4 cosine of pi minus 0 because x and sine both go, and then minus 1/4 cosine of 0. Nice, we got it. So sine pi is 0, so that dies and 0 is gone. Cosine of pi is -1, so we have -1/4 minus another quarter is -half. We all got -half? So there it is. Yeah, I know. Yeah, everyone can do calculus in this room. It's just no one can do the algebra and pre-calculation. But that's what it is. I mean, welcome to trick-driven course. And this is not even scratching the surface of the next two sections. Next one? Okay. Something interesting, right? Something interesting with trig. All right, so one more of this, and then the evil problem, and then we're done with this. Wow, this is great. We are moving really slow with this class. I mean, with the course, we are behind. We'll have to pick up the pace and do like 3 sections per class if we are going to move this slow to cover the material. Yep. So integral of x sine 3x from 0 to pi over 4 dx. All right, this is pretty much the same as the previous one. Got it?
Just wondering if I got it correctly or not. Like the years that you would like the divide by 3. Would it always be like that pretty much?
What do you mean?
Like be like when you do an integration, it'd be like it would be like spread to the center of the board. And like honestly, it's how you when you do the integration, you do the derivative type of rule.
Well, that's the next step. Type of this particular method have 60 methods. So what the determine this method is always going to solve that So the second half of it, yeah. What's that? So I chose the right on this time. I switched it last time.
Oh yeah, no, me too. That's why I stopped.
Oh,
Before I
really?
kept going. I literally got to like here and I started getting this and I was like, we're gonna leave that thing. Did you also have like the little expert trying to sign it? Yeah. Exactly, me too.
Yeah. But I went through it and I tested against his.
All right, what do we have? We have, okay, so we're gonna fly to this one and then do the other problem. I'm just going to present because it's too spicy, and then we'll move on. So this one is, again, standard setup u equals x, dv equals sine 3x dx. You gotta write this dx at the end over here. It's not there for decoration. du equals dx, and v is equal to negative cosine 3x over 3. Put the arrow there to help us with the formula. We have negative 1/3 x cosine 3x. Minus and minus will give me plus. Integral 1/3 goes outside, and then we have the cosine 3x dx. It is from 0 to pi over 4. We have negative 1/3 x cosine 3x, and then we have integral of cosine is positive sign, so we have plus 1/9 sine 3x, computed from 0 to pi over 4. So now we have, when we plug in pi over 4, we get negative pi over 12 cosine of 3 pi over 4 plus 1/9 sine of 3 pi over 4 minus 0 because that's, or plus 0, whatever, and then another minus 0 because of the sine of 0 is 0. Now to find these values, I know that the pi over 4 is root 2 over 2, but is it positive or negative, right? The fastest way to determine that is to draw sine and cosine graphs, because you just need a location. You know what the value is. You just need the location to see whether it's positive or negative. So for cosine, 3 pi over 4, we know this is a pi. 3 pi over 4, this is pi over 2. So 3 pi over 4 is here, right? So that's negative. So it's negative, and negative gives us positive. So pi over 12 root 2 over 2 plus 1/9. And then sine is positive. So positive root 2 over 2. And we have the answer. The answer is you can factor out 6 root 2 over 6, right?
We're getting to 1/9.
1/3 time 1/3 times 1/3. Root 2 over 2 pi over 4 plus root 2, 1 over 3, right? Ta-da!
In regard to the selection of U and DV, obviously you can play around with it, but Typically, if it's the x value.
Yeah, the general rule is for sines, cosines, and e to the x, x is u, and then for ln, it's not. But then there's just so many other things with the square roots and stuff. When these few of these show up, you know immediately what to do. But then when something is, generally the way I like to look at it to make the choice is, what are the things that I can integrate and what are the things that I can't integrate? So if I had the ln, I want to put ln into derivative because I can differentiate that, because we can differentiate everything, but you can't integrate everything. So I keep the stuff that I can't integrate if I have it in thing like inverse sine or ln or something. I keep that for derivative part and the rest for integration, right? Because you can always have at least just dx for integral, right?
Yeah, yeah. So what if you switch those values? Will that be a completely different?
Yeah, and that's exactly what the lab addresses. Okay. The lab is asking you to make wrong choices, and then you see how stuck you get, because the problem cannot be solved. So there will be a lot of problems, maybe 5, 6, 7 problems that are purposely derailing you. And then after part A, part B, part C, part D says, why were these wrong, right? And in each case, they're wrong because they give you A, you can't integrate, B, you integrate, but now the new expression is just insane, right? And then you have to do another step. So in each case, it becomes much worse. And that is, again, training and, right, practice doing over and over and over and over, right? Over 1,000 times to do it. All right. All right, so now we'll get to the one that I call the evil one. And this problem looks like this. Now, if you haven't noticed so far at your, as we were doing this, most of the time you are picking u equals x because, or x squared or x cubed, and you are picking that because the derivative will eventually kill that part of the problem, and then you just have the other thing to integrate. So if you go back to our, let's say, first problem that we ever did and the second problem we did, the reason why you have to use a different technique for this problem is because you have that x in front of e to the x. You know how to integrate each one independently, but together it can't be done. So we assign x to u because u will be differentiated and that x will be gone. So if you compare the original integral, come on, original integral and the integral that you got later, they're pretty much the same. There's no x. That was the problem. Moving to the next example, which is the same thing, looking at the original integral and the integral we got later, that x is gone. And that x dies in the procedure here with the integral, with the derivative. So in almost every problem, we were focusing on eliminating one of these two guys. And as soon as one of those two guys was eliminated, we were able to solve the problem. But think about these. Would any of these two functions, when you do repeated either integration or differentiation, would any of them ever go away? And the answer is no. So the common sense is walk away, because if you keep integrating, if you keep differentiating, right, it cannot work. But there is a really clever trick that is used here, and that trick helps us actually solve the problem. So the way I'm going to do this is I'm going to actually do integration by parts twice here, and after the second integration by parts, I'm going to take the entire integral and move it to the left side and add it to this. It's a really, really crazy trick, but it works. So u equals e to the x, and dv equals sine x dx, and then du equals e to the x dx, and v equals negative cosine x. And now we plug everything in and get negative e to, so this is equal to, right, e to the x cosine x, and then plus the integral of e to the x cosine x dx. So it looks like that we haven't achieved anything, right? Because we did not lose any of the two functions. It's pretty much the same difficulty as the original problem. Now, whoever did this the first time said, right? Clearly insane person, right? Let's just do it again because it didn't work the first time, right? so u equals e to the x. dv now is cosine x dx. And du equals e to the x. And v is equal to now sine x. And we do. Now, we can't forget to copy the first part. Negative e to the x cosine x plus. And now we have another by parts. So it's e to the x sine x minus the integral of e to the x sine x dx. So at this point, you are back to where you started, right? And here is the brilliance of the trick. You take this part here and you add to the original problem. Because this is your left-hand side and the whole thing over here is right-hand side. So it's just like moving x from one side of the equation to another side of the equation. So add this to the left-hand side. And what you end up with is two integrals of e to the x sine x dx equals to negative e to the x cosine x plus e to the x sine x. And all I need to do is to divide both sides by 2. You see how awesome this is?
What type of theorem does it prove anyway? Or what type of formula did you use for e of x sine of x?
I didn't use. What do you mean? What type of formula?
E sine of x. How did you get negative e to x? E to negative cosine x plus by e x sine x.
Wait, hold on a second. I did integration by parts twice.
Okay.
This came out of the first integration by parts. This came out of the second integration by parts, and then I moved this term to the left side, and when they add, you get 2 of them equal to the leftover, and then you just divide both sides by 2, factor out e to the x, and it's all done. It's amazing. The first time I saw this problem, my jaw dropped because it would never occur to me to do something like that. It's a really clever trick. Left-hand side of the equal sign, which is the original problem. Yeah, so technically, you know, if what happened here is we have x equals to, I don't know, 3a minus b minus x. And then you took this x and you move it to the other side to get 2x equals to 3a minus b. That's technically what happened, except these expressions are much larger. But from algebra level, if you simplify everything, this is literally what we did. And then divide both sides by 2 to get. So it's amazing how the whole thing worked. So that's a fun problem for you to consider. If you want to learn it, you learn it, and then you control others. When they tell you, you're out and it's having fun, they say, what do you know? Put this on a napkin, ask them to solve it. And then use next 45 minutes to annoy them to explain how it's actually done. I think that's a point. You can go home and play video games in peace without anyone bothering you. That's it for this section. We have to go start doing the trig stuff for fun.